first of all wanted to report that we had some action last night. So I promised we would post the updates to those Schrödinger papers, the 1D paper and 2D paper. So finally we posted those updates. We were strongly encouraged by good friends that there should be more details in there. So the one-dimensional paper has increased by 10 pages, and the two-dimensional pages by 1/2, of course, 5 pages. And then we also got around to post this other paper on the ultra-hyperbolic problem, which is joined with the Mihaela Ifrim and with the Ben Pinot. All right. So last time I was telling you about the one-dimensional problem, and I didn't quite finish telling you everything. Especially, I did not get to wrap everything nicely at the end.
Daniel, just to clarify what you said, so the thing you are speaking in the 1D is the one you post, let's say yesterday or.
Yeah. Okay. No. The thing that I'm mostly will be speaking today, we updated it. We did not just post it.
Okay.
Yeah. Right. But so coming back to the one-dimensional paper, so I'll still tell you a little bit about the quasi-linear Schrödinger equation. But I'll write the equations on this board, and I'll write them in the way that I will use them later also in higher dimensions. So it's the same equations, 1D and 2D. So we had this equation QNLS, which was I dt minus, let's say, Gij of u di dju is equal to some nonlinearity of u grad u. I remind you that everything is cubic in what we do, and then we had dq and ls, I dt, some brackets in here, minus Gij of u and du, di dj. U is equal to n of u du. So here in higher dimensions we have a metric. One can look at two interesting cases: the elliptic case when the metric is positive definite, or what I was telling you about the ultra-hyperbolic case when the metric doesn't have a signature, doesn't have a sign. But in one dimension, of course, there's only the elliptic case. All right, so I'll remind you that I'm writing the second equation just because the results that I'm telling you about apply just as well to the second equation, except we look at this one at regularity level 1 higher. So here we have u of 0 is equal to u0. This is in HS. And there's a quick computation that we did last time. So we have the critical exponent, which is n over 2 for QNLS, and then n over 2 plus 1 for DQNLS. And then the results that I was telling you about in here apply for s greater than n plus 1 over 2 for Q and LS, and they apply for s greater than n plus 3 over 2, 1 higher for DQ and LS. So from now on I'll stay with the Q and LS, and I wanted to remind you a little bit the setup that we had in one dimension. So we have a solution U. We represent this in a Littlewood-Paley decomposition, and then we try to get estimates separately for each of these species, and we put our initial data under a frequency envelopes. So let's say epsilon, c lambda, lambda minus s. So lambda minus s because of the HS regularity. Epsilon is the small parameter, and c lambda is the actual frequency envelope, and this is normalized in small L2. So norm of c lambda in L2 is comparable to 1. And then the estimates that we wanted to prove were, first of all, the energy, which is normal v lambda in L infinity L2, smaller than epsilon c lambda lambda minus s. Then we had the Strickard's estimates, and that would be u lambda in L6, smaller than, and here we had two versions of this, epsilon c lambda lambda to the power minus s, or epsilon c lambda lambda to the power, and here was a funny power, minus 4s plus 1 divided by 6. And this first number is for local well-posedness, and the second number was for global well-posedness. So we have a stronger estimate locally in time, but a weaker estimate globally in time. And then we had bilinear L2 estimates, and those came in two varieties. One was unbalanced, when we have two different frequencies, lambda and mu. We look at u lambda, u mu. I'll put a bar, just mu, wanted to say, in L2, smaller than epsilon square c lambda c mu, lambda minus s minus 1/2 mu minus s. So here you see the gain of 1/2 derivative at high frequency. So let's say lambda is larger than mu in here. And then the balanced version of this, which was norm of u lambda, let's say dx u lambda bar in L2, smaller than epsilon square c lambda c lambda square, lambda to the power minus 2s plus 1/2. And so this is for balanced frequency interactions. So our global solutions at the regularity level that we have on the other board, our theorem says they satisfy all of these estimates. And so I was telling you last time about how we prove these estimates. And this is all under a big bootstrap umbrella. We assume that all of these estimates hold with larger constants, and then we want to eliminate the large constant. And what I showed you last time is that we look at modified, let's say, density flux energies, energy estimate, energy relations, if you want. And we did this for the mass and for the momentum, and in particular dtm lambda sharp of u was dx. And maybe let me not write this twice. So we had the original mass functional at frequency lambda, and to this we added this mass, this quartic correction, let's say b lambda of u, and this I'll put a 4 because this is a 4 linear form, is equal to dx, and here we had the essentially the momentum, and here we also have a correction, r lambda 4 of u. And this is not an exact relation. We have some source terms in there, and the source terms I showed you, they are of two forms. Let's say you have some error terms. Let's see, this was not r, this was q. We have some error term which is 4 linear, but which only contains transversal interactions, and then we had some error term which is r lambda 6, which contains 6 linear terms. And part of the thing that streamlines this analysis is we want to think about these error terms perturbatively. In other words, we always try to estimate these guys in L1. And the first guy is 4 linear, so to estimate it in L1, you use 2 bilinear L2 estimates. And that's why you need this transversality, so this only contains transversal wave interactions. Whereas here, you can still use transversality if the frequencies are unbalanced, but if the frequencies are equal, then you have to use the L6 estimate 6 times. So this is the relation for the mass. And then we had a similar relation for the momentum, plus b lambda of u. This maybe depends on m. This depends on, this is associated to the pressure, and so on. So this looks very much the same. All right, and so what I did not get to tell you last time is how we close things. And you can close the energy estimates directly by looking at this. So to estimate, let's say, a norm of the solution u frequency lambda in L infinity L2, all we do is we integrate, let's say, the mass relation. All right, and this gives us the difference in the two values of the masses at 2 different times. So this gives us m lambda plus b lambda for m evaluated between time 0 and time t in the integrated version. And then when you integrate, the flux disappears, and you get the integral of r's. And this is a double integral dx dt. And this L1 norms are in x and t. So your error is estimated in L1, so it integrates nicely. And then you get the change in mass. Not exactly the change in mass, this is the change in the modified mass. Okay, so you want to get from the modified mass to the mass, and then you think about this term perturbatively. And estimating this term perturbative is perhaps the easiest thing of all, because this happens at fixed time. So you just have Sobolev spaces and multiply functions in Sobolev spaces. There's nothing fancy to that. All right. Plus this b lambda, these guys are balanced. So all the entries are at frequency lambda. The same for q lambda. On the other hand, if you look at the r's, these are not necessarily balanced. So you have entries at all frequencies. So estimating these r's is extensive. It's a lot of work. All right. So this is how you close the energy estimate. And now once you have the energy estimate, you get the bilinear estimates. So to close bilinear estimates, I told you about that interaction Moravec's functional, let's say I of uv, which was integral when x is greater than y. Think of u as depending on the variable x, v depending on the variable y. This is m, this is the modified mass. So this is our m sharp of u, p of v, minus p sharp of v, minus m sharp of v, p of u, dx dy. All right, and then we said when we compute the time derivative of this interaction Moravec's functional, we get a spatial integral with a number of expressions. So if you do the analysis at the linear level, you get a 4 linear form, because you have here you have 2 entries, so this is 4 linear. So your leading contribution here will be 4 linear. And then we have a 6 linear term. and then we have an 8 linear term, and then the error k, which is generated by the source terms. All right, and so we said we want to use this this Moravec's functional in order to gain control over the bilinear estimates. And what I did not get to tell you in full is what successive choices do we make in here for the functions that we put for u and v. And so we take maybe 3 scenarios. The first scenario was the balanced diagonal case. That was for u is equal to u lambda, and v is also u lambda. So this applies to exactly the same object. And what I showed you last time is that if we have this scenario, then what we get, the mileage that we want to get out of this is the J4 component. This will give us the bound for d lambda u lambda bar in L2 square. So there's lots of commutator terms I explained last time, lots of errors to handle, but at leading order this is J4. Then J6 at leading order modulo error terms. This is essentially like the norm of u lambda in L6 to the power 6. And this is where we use the defocusing condition. All right. And then J8 and K are perturbative. All right. And so what we do is we integrate this relation. And the way we think about this is we get integral of J4 plus integral of J6 smaller than, and on the right we have I evaluated between times 0 and t plus the perturbative terms. All right. And so we use this to estimate the integral of J4 and integral of J6, and therefore get the bilinear L2, and then get the L6 bound from there. All right, and then the I, to estimate the I, all you need to have is the energy estimates, and the energy estimates were closed earlier. All right, so that's the leading term in there in terms of the on the right-hand side, and that has the bootstrap has already been closed for that. So this is to ensure that we don't run a circular argument. So this is one scenario. The second scenario is the following, and now I'm coming back to the estimates in here. And I'll add something that I omitted at the first reading. So I was telling you that when we look at these bilinear estimates, we would like them to have invariant with respect to translations, but we have 2 translation parameters a priori, one for one variable, one for the other variable. So we would like to allow one of these guys to be translated. This is easier done in the unbalanced case, but in the balanced case, if we want to translate, then there is a price to pay, which is natural somehow, and it's also reasonable in the context of the big argument. And that motivates the second case in here. This is the shifted balance. Okay, so now our 2 entries u is equal to u lambda, but v is u lambda shifted by x naught. All right. When we put these 2 guys inside of our Moravec's estimate, then our J4 will give us the same as in the linear case, norm of d u lambda bar x0 in L2. So we get mileage from J4. But now for J6, we no longer have a sign. However, in the first case, we have already estimated the norm of u lambda in L6. So now we have it in our pocket. And then J6 becomes a perturbative term. So now our identity reads integral of J4 smaller than I evaluated between time 0 and t plus integral of J6 plus and so on. Everything else is still perturbative, but the novelty here is that this is also perturbative because now I can estimate this using the L6 estimate, which I have closed earlier. All right, so this was second case. And then we have the third case where we look at unbalanced case. And this is the easiest part. And here u is equal to u lambda and v is equal to v to u mu x0. So both at a different frequency and a different location. And then, as in the second case, we only use J4 and everything else is estimated perturbatively. So that's how this bootstrap loop closes. And so at the end of the day, in terms of global well-posedness, you get this energy estimates for the solution, for the daddy components of our solutions, u lambda. On the other hand, if we look at the local well-posedness part of our result, then we need energy estimates. So this corresponds to HS if you want. U lambda in HS, and at the same time, we also want to have energy estimates for, let's say, V lambda, which corresponds to the linearized equation. In L2. So the linearized equation, we just treat it in L2. This means that this entire philosophy, we have to implement it also for the linearized equation, except that at the linearized equation, you lose some symmetries. And because you lose some symmetries, that's where you need this stronger L4, the stronger L6 norm. So Strickhart's estimate without loss. All right. And one theorem in here that I'll just state for now. Strickhart's estimates, let's say lossless Strickhart's estimates hold for the paradifferential equation. Let me just remind you what the paradifferential equation was. It was I dt. So this is frequency localized plus, and then we have derivative. We have this truncated metric, which we call g less than lambda. D. This also holds in other dimensions. So ij, the way we write the paradifferential equation, not the theorem. dj v lambda is equal to f lambda, all right? And the secret in this theorem and the reason we can apply it is to have a good place where you put the source terms f lambda. This is something that I will tell you about on Friday. I'll just say for now that the good place to put this f lambdas is very, very non-standard. And this is because we need the space of source terms to be really big because we have lots of interesting source terms to put in there. And if you don't make the space big enough, then we cannot write our linearized equation as a paradifferential equation with a perturbative, if you want, source term. All right, so this is what happens in terms of estimates. So as I said, I'll tell you about this tomorrow. And then the final bit that I wanted to mention in terms of well-posedness. How does the proof of local well-posedness goes? This proof of local well-posedness has two pillars. There's two bits of information. Maybe let's call it three bits of information if you want. One, we have energy estimates for U in HS. So that's basic for any problem where you want to prove well-posedness. You need to have good energy estimates. Secondly, you also want to have energy estimates for U, for solution U, in higher Sobolev norms. Okay, so that if you have more regular data, then you know that you get a more regular solution. And important is that in these energy estimates, they do not depend on the higher Sobolev norm. The lifespan and so on depend only on the smaller Sobolev norm. And the third pillar of this is to have energy estimates for, let's say, differences, which in this problem is the same as looking at the linearized equation. In our context in L2, this L2 we can wiggle a bit if you want. We can make it a range of Sobolev spaces, but really for local well-posedness, that's all you need. And the claim here is that if you have this 1 plus 2 plus 3, and maybe plus a local well-posedness result for regular data, then you get your local well-posedness result at the threshold that you want. And so there's a little bit of a story to tell in here. Remember, this local well-posedness is a quasi-linear kind of local well-posedness. So you want to get not only existence and uniqueness, but you also want to get continuous dependence of solutions on the initial data. I can make comments about each of these bits. In terms of existence, as I said, we are assuming that we have solutions already for more regular data, so we have a good starting point. And then to get rough initial data, we can get the rough solutions as the limits of smooth solutions. Okay. Uniqueness is also a place where a story can be told, because there's no clean, if you want, no unique way you can phrase the uniqueness. The most general way you can phrase the uniqueness is to say, oh, there's a unique HS solution. And that's way too vague for this problem. Unique HS solution is what you might call unconditional uniqueness. You have a single solution which is continuous with values in HS. This is not something we can do. And the kind of uniqueness that we can get for this kind of problems is a weaker form of uniqueness, where we say, well, we can get uniqueness. The next stage would be to say we can get uniqueness for solutions which not only stay in HS, but satisfy our full family of estimates. And this is doable, but we didn't even do this, all right? And what we did instead is, when we looked at these rough solutions, we said, well, there is a unique limit of smooth solutions. And that gives you sort of the unique candidate for what you define then to be the unique solution, all right? So that's the other thing. And then in terms of continuous dependence, if you're on the Hadamard well-posedness. This is also a long story, which goes back to Kato in the 70s. So Kato was the first one to prove this continuous dependence in systems of nonlinear hyperbolic equations. The argument of Kato, if you look at it with today's eyes, is maybe not the easiest to read because it's phrased in terms of a little bit in terms of semi-group theory. But so let's say Kato, write him down. But then if you go to do a little bit of search and go to Tao's blog, you will find Tao's interpretation of Kato's proof, which is kind of the same argument, but at least written in our modern terminology, if you want. Then there was a paper a number of years ago, maybe in the 80s, 90s, I don't know, a paper of Bona and Smith, which many people cited as the source for continuous dependence, but really this paper mixed too many things in terms of getting a continuous dependence, mixed regularization of the data and regularization of the flow for a very specific equation. So maybe that's not the best source for continuous dependence. And then we have the more modern way that we have been using in the last, I don't know, 10, 20 years for local well-posedness. Together with Mihaela, we had this summer school maybe 4 or 5 years ago, so we wrote a set of notes explaining how this should go. So this is maybe 2020. We called it a primer for local well-posedness, where we showed how one can phrase this continuous dependence proof in this language of frequency envelopes, which is a very nice way to wrap the proof in. And then maybe if we go to 24, together with Thomas Alazard and Nicolas Burk and Mihaela, myself, and Claude Zueli, we took this sort of description of the method on a case that we did in our primer with Mihaela, and we put it in a more abstract footing. So this is 2024. And so right now I think these are the two places to go to. And what we did in these papers is essentially we follow for the well-posedness the recipe coming from here. And that pretty much concludes what I wanted to tell you about the one-dimensional problem. All right, so now I'm happy that I finished my one-dimensional game plan, and then I'll switch to 2 dimensions. All right, and so for 2 dimensions, we still have these equations. The numerology here is written in 2 dimensions, in all dimensions. And the nice thing in 2 dimensions is that I can go a little bit faster in that I don't have to revisit a lot of the things that I have been already telling you about. So let me remind you the conjecture. All right, so the 2D conjecture simply states that 2D dispersive cubic problems. So you take a 2D dispersive cubic problem.
Daniel, can I ask you a question?
Yeah.
So sorry, I am writing this like 1 minute later after you said it. But so when you do the continuous dependence, you are essentially saying that if you take 2 solutions, which are the ones that you constructed as limits of the smooth solution, then if they are closed at the beginning, they stay closed, right?
Well, if you phrase it this way, it almost sounds like uniform continuity, and there's no uniform continuity.
Yeah, but with the appropriate form. But, no, but I'm trying to relate that to the fact that you decided that you said I can do the uniqueness the right way. I mean, when I say that, it's my opinion, but you see what I mean. And you decided that you were lazy and you took it as just as the unique. I don't like the limits of the smooth solution. So I am happy that you said that you can actually do it the right way. And now I'm saying if you can do it the right way, for the continuous dependence, it's not exactly the same way the same thing to say I take the solution that I constructed and I take a solution I constructed and I take another solution which is in the same class, but it's not necessarily the one that I. But
which still satisfies all my estimates, and including the frequency envelopes.
Yeah, well, there is a question about the frequency envelope, which is a different question, which is that. Is it really different to say that you are essentially requiring some kind of uniform decay of the tails in lambda?
In some sense, right? But because here you implicitly, when you put the frequency, you include some square summability.
I understand what is it that they are with the frequency envelope. To me, it is the uniform decay of the tail, and then. No.
That's one piece of it, and of course that's the piece that matters for continuous dependence. Yes. Right, the uniform decay of the tails. That's.
So it looks like you can do what I want, which is fine.
I would say so, yeah. Yeah.
I think it's still worth doing at some point. Maybe you want to find a grad student to do it, but.
Well, one can even go a little bit farther and ask to relax a little bit. I mean, not maybe get full unconditional uniqueness, but somehow somewhere in between unconditional uniqueness.
I'm fine with the intermediate step, but the fact that you take the only limits of smooth solution, there are enough examples where that can produce bad stuff from other hyperbolic models, so somehow.
Yeah, but this is.
Yeah, of course, but see, what I mean is that some people might get distracted by that at some point. And,
right.
It's a little bit when at the time people were saying, local well-posedness means uniform continuity, so and then it took 10 years to unravel that and to actually make people understand that no, it was not, that there is a difference between the two. So I'm sorry, I feel strongly about this. I think we agree.
Yeah, I think we agree. Right. When you prove a well-posedness result, initially you want to get some sort of uniqueness with continuous dependence, right? And maybe the next step, like say for a graduate student perhaps, is to refine the result. Okay, coming back to the conjecture. So we start with the two-dimensional dispersive cubic problem, even higher dimensional, but higher is easier, so that's why I'm stating this in 2 dimensions. And cubic problems which are semi-linear in 2D are easy for small data, so we're going to make this problem quasi-linear. Okay, so make it harder. And then the conjecture says small data, small, let's say HS data, implies global well-posedness plus scattering. And I'll remind you that this is the classical scattering. At infinity, your solution looks like a solution for the corresponding linear flow. And so our task in this paper that we have just updated last night, it was to see if we could prove this conjecture for these 2 equations that you have in there. And again, the same thing that I was telling you for the one-dimensional problem, something that we learned along the way, is that our strategy to prove this global well-posedness, in effect, also allows us to improve the local well-posedness. So let me state these 2 theorems separately. So the first theorem says that we have local well-posedness for Q and LS. For S greater than n plus 1 over 2. And here n is greater than or equal to 2. And then the second theorem, this is the global QN LS. This is the global well-posedness result. Okay, and here we have two versions of the theorem, maybe three versions of the theorem. First, S greater than n plus 1 over 2, and this, as written, applies for n greater than or equal to 3. All right, and then we have S greater than or equal to n plus 2 over 2, so we go half derivative higher for n is equal to 2. And of course, we were not happy about this, and we thought to fix this, to put here also n plus 1 over 2. And the way we could do this is by adding a supplementary assumption, plus assuming that the equation is conservative. And this is for n is equal to 2. So with a little bit of structure, we can get to this threshold also in dimension 2. Let me remind you what the conservative assumption is. This was a cancellation condition at the level of the phase rotation invariant component of the cubic part of the nonlinearity. Here, we're not assuming that the nonlinearity has phase rotation invariance, still we can get these global results. But the phase rotation invariant part is still the most important one, and that is reflected in this component of the two-dimensional result. And maybe for a little bit of perspective, here there is, maybe I should say, so these theorems, we also proved them with Mihaela and with Ben in the ultra-hyperbolic case in the paper that we posted last night. And the statements of the theorems are the same, though there are some interesting difficulties in the proof in that case. And that will come up when I wanted to tell you a little bit about the history of this. First, these are the first global well-posedness results of this type, but there were local well-posedness results before. What were those local well-posedness results? So the first local well-posedness results were Koenig and Ponce and Vega. So that was maybe 2003 to 7, something like that. So what they did is they looked at a regular and localized data. All right, and then the next threshold was work that I did with Jason Metcalf and Jeremy Marzola. So let's call this MMT. And so here we figured out how to do this in translation invariant Sobolev spaces, so just in HS. But our threshold was S greater than n plus 3 over 2. And so you should compare this n plus 3 over 2 not with this one, because this is for, sorry, what happened here? Right, this is for DQNLS. You should compare that with this one, which is in the theorem upstairs. So our new result improves our earlier result by a full derivative. The other part of the story, maybe in here, which I mentioned a little bit before, is that these results were for small data, especially my result with Metcalf and Marzola. If you want to look at the large data problem, you need to have this non-trapping condition for the initial data. So large data requires non-trapping. And non-trapping is very easy to explain. You look at geodesics for the G metric, and you ask that every geodesic comes from infinity and goes to infinity. So If you have small data, non-trapping is automatically satisfied. If you have large data, you need to put this as an assumption for a large data result. So why do we care about this? Because our results in these papers are small data results, right? But we're looking at small data in this HS where S is greater than n plus 1 over 2. Having smallness in this space does not guarantee smallness in this space. So our data could very, very well be large in this space. So if we want to use this result, which we do, then we want to know that non-trapping holds when S is greater than n plus 1 over 2. All right, so what's the difficulty? Well, if S is greater than n plus 3 over 2, you can make sense of the geodesics. It's very important. And then you can say, well, non-trapping means that for every geodesic, it comes from infinity, it goes to infinity. If you're only at S greater than n plus 1 over 2, if you write down the equation for geodesics and you want this equation to be meaningful, then at the very least you need to know one derivative of the metric, right? If you want to make sense of uniqueness of the geodesics, you need two derivatives of the metric, right? Well, n plus 1 over 2 is the borderline case where you can even make sense of one derivative of the metric on a curve. And so below this, there's no clue even what does non-trapping means. And so that's the reason we believe this result, this threshold that we have obtained, should be the sharp local well-posedness result. Possibly, we think, one could fiddle with trapping, and if you try to go below this, violate the trapping in a quantitative way and show that such a result cannot hold below this threshold. This is speculation, right? This is a conjecture, if you want, that this result, that going below n plus 1 over 2 is impossible. Going exactly at n plus 1 over 2, that's a borderline problem which we don't have a clear idea how it should go. So could be very hard. Okay, so these are the two-dimensional theorems, and exactly as in the one-dimensional case, they come together with a family of estimates. And unfortunately, I cannot use exactly the estimates from here, so I have to redo this board. We still take a little Wood-Paley decomposition of the initial data, and then we want to write down bounds for the solution in terms of this little Wood-Paley decomposition, in terms of these frequency envelopes. Maybe the energy estimate rests unchanged, but 6 is no longer an interesting number in dimension 2. In dimension 2, the important number is 4. The L4 is the critical Strickhart's estimate. And so let me let's see. I could I need more space, so I'll do it here. And I also want to do it in a slightly different order. So we have our estimates. And we start with the energy. And this is the same. U lambda L infinity L2 smaller than epsilon C lambda lambda minus S. And then I want to write down this bilinear estimates. And I want to write down these bilinear estimates in an unbalanced version and a balanced version. So here we look at u lambda, u mu bar. We try to measure this in L2, and this is smaller than epsilon c lambda c mu, lambda to the power minus s minus 1/2. So we gain our half derivative at high frequency, but then we have to pay with some low frequencies, minus s plus n minus 1/2. All right, so this term does not exist in one dimension, and this is lambda greater than mu. And again, as in the one-dimensional case, this is the easier setting because we're looking at two waves with different group velocities, so their intersection is always transversal. And we don't really think of this as a Strickard's estimate, like I explained before. We think of this as a transversality estimate. All right, then we have the balanced bilinear estimate. And by the way, this is also important, making this invariant with respect to separate translations. So balanced bilinear estimates. So this would be, so here I want to look at u lambda bar. Maybe translate this one. And then here we want to put a number of derivatives. And the correct number is d to the power 3 minus n divided by 2. And this is smaller than epsilon square, c lambda square, lambda to the power, whatever power we have in here, coming from scaling. I don't want to open my tablet right now. You can easily figure it out, in effect. Let's say n minus 1, 3 minus n. That would be minus 2s plus a half, something like this. All right. In any case, let's take that we should have the correct number in there. And let's, if we examine this in different dimensions, we see that this exponent in here is negative in dimension 2, and it's 0 in dimension 3, and it's strictly positive in dimension 4 and higher. And I was telling you earlier about the way this kind of estimates came from interaction Moravec. And so this goes back to that history. And the I team essentially did the case of dimension 3 and higher. And there it was critical that this exponent that you see in here is implicitly in their computation is non-negative. So that gives, in particular, that gives an L4 bound. So this implies L4 for u lambda if n is greater than or equal to 3. Whereas if you try to do this in dimension 1 or 2, our guide for that was the work of Fabrice and Luis Vega. So this is the balanced bilinear case. Now, I was telling you that the L4 is the important number in here, the exponent 4. And you see that we get this exponent 4 for free in dimension 3 and higher. So in dimension 3 and higher, we didn't even have to worry about the Strickard's estimates separately, but we care about dimension 2 in here, and in dimension 2 we do not get an L4 estimate in here. So this is why we have the next line, Strickard's estimates.
3 minus n minus 3.
Sorry.
The exponent of 3. Yes.
3 minus n?
Oh, okay. So it's positive for n is 2.
It's positive for n is 2. Yeah. Did I say it the opposite way? Sorry. Yeah, it's positive for n is 2.
We understood.
Clearly.
For n equal 1.
Yeah. Right. Right, exactly. Positive is bad. Negative is good. Keep point, right? All right. And then we have the Strickard's estimates. And I'm glad I did not erase this board. And the Strickard's estimates, so you have this Strickard's exponents, and you try to estimate norma of the solution U in LP, LQ, where P and Q are sharp Strickard's exponents. And ideally, you'd like to have this smaller than epsilon C lambda times lambda to the power minus S. That could be in a perfect world. It's not a perfect world. So here we have a loss in the Strickard's estimates. And our loss is exactly 2 over P derivatives. And so, Strickard's estimates, well, first of all, we can compare this with the one-dimensional result. In the one-dimensional result, for local well-posedness, we had Strickard's estimates without losses. But for the global result, we have Strickard's estimates with losses. Here, we have the loss both for the local and for the global result. Okay? And the loss is 2 over P derivatives. There's a long story about Strickard's estimates with losses, and I'll tell it on Friday. But so this loss is sort of a fairly large loss. But the good news is we don't really care so much about the Strickard's estimates bit. The only reason we care about the Strickard's estimates is for the case when dimension is equal to 2 and when the two exponents P and Q are equal to 4. So we only need this for n is equal to 2, P is equal to Q is equal to 4. And in other dimensions, the Strickard's estimates is something that we prove, but we never use. So I was telling you that everything gets put into a big bootstrap loop. So we assume that all these estimates hold with a large constant. Here, we put this large constant only for 2 dimensions, P is equal to Q equal to 4. Everything else, it doesn't need to go in the bootstrap loop. And the argument in the higher dimensional case is still a big bootstrap argument, where you...
For the 2D case, the fact that you don't get the L4, and because in the flat case, of course, you can recover it by essentially erasing the derivative by playing with the Galilean invariance. And so, conceivably, it could be doable here, provided that one can play this appropriate approximation of the Galilean invariance in the variable coefficient case. Right. I don't see it as being something that should be not doable. Then whether it's compatible with the kind of hypothesis one has on the metric, I don't know. But.
Well, I mean, the classical hypothesis that one has on the metric in order to get, let's say, Strickard's estimates without losses are quite drastic.
I'm just talking about the L4 bound from the bilinear stuff, not the full range of Strickard.
Oh, trying to get L4 bounds here.
Yeah, just L4 and L2. I'm trying to balance.
This seems really out of reach in 2 dimensions to try to get an L4 bound. I agree that if you had constant coefficients, then you could use this balance bounds to prove it, but if you have variable coefficients, then things get very bad very fast. Also here, maybe I should put 1 plus lambda x0, the same as in the one-dimensional case.
I can tell you later.
There's a lot that one can say about this, indeed. All right, so we have this estimates, we have this big bootstrap argument, and so looking at the clock, it's a good time for a little break, and 5 minutes, and then I'll tell you about the proof of this after the break. So just as in the one-dimensional case, most of the work is done on the paradifferential equation. So you want to work on, first of all, we're doing nonlinear PDEs, but secretly at some point we do some linear estimates. And so we want to work on this linear paradifferential equation. And this linear paradifferential equation has the form, the same one as we had before, IDT plus D J G Jk less than lambda dk applied to V lambda is equal to F lambda. And this metric, maybe let me remind you what we choose it to be. This is P less than lambda of G of U much less than lambda. All right, so and this is so that we do not include any balanced interactions in here. This is less important in higher dimensions. It was more important in one dimension. And then using this linear paradifferential equation, we can write our full equation as a paradifferential equation with a source term, IDT plus dj g jk less than lambda dk u lambda is equal to some n lambda of u. In the one-dimensional case, we had to split n lambda a little bit more. In dimension 3 or higher, that's all that happens in here. In dimension 2, we need to split this n lambda into, first of all, into two portions. A cubic term plus a higher order term. Okay. And this splitting is important. We always have to do it for the global result in two dimensions. And then the proof forks depending on whether we want the sharp regularity and the non-sharp regularity for the 2D result. If we allow S to be large enough in 2D, then this C lambda also goes into the perturbative box using this L4 Strickhart's estimates. But if we are in this other situation when S is just greater than n plus 1 over 2, then the L4 estimate is no longer powerful enough, so we throw it away. We don't need it anymore, but then we have to do something else. And then we take this C lambda and we split it into 3 portions. So let's say the one expression that carries most of the resonant interactions, where we have the phase rotation symmetry. And then we have another term where we have 3 U entries. And then, so write all of these other terms, okay? And then the interesting observation is that we can use this unbalanced bilinear estimate anytime we have transversal interactions, okay? So in here we have two kinds of interactions which are good. And then the other kind of interactions which are good are non-resonant interactions. For non-resonant interactions, you can do corrections to fluxes and divergence and to densities and fluxes. So let's say non-resonant interactions are good. So when you look at all the possible candidates in here for the cubic nonlinearity, you try to put as much as possible in the transversal box and in the non-resonant box, and then see what is left. Okay? And if you do the algebra, and algebra is fairly simple, because all you need to understand is what happens, what are the interactions that are both not transversal and resonant. Okay? And so you're looking at this, I can write it in here, system with two equations with two unknowns, xi1, let me put the indices up, minus xi2 plus xi, let's say plus minus xi3 plus minus xi4 is equal to 0. And then xi1 square plus minus xi2 square plus minus bad notation. Let me put the indices down here just to confuse you. Plus minus xi3 square plus minus xi4 square is equal to 0. The signs are matched between these two equations because plus or minus depends on whether you have a complex conjugate or not. And so non-transversal means that at least 3 xi's are equal. Because if only 2 xi's are equal, then you have 2 pairs of unbalanced interactions. So if you don't have to look at all solutions for these equations, this will have lots of solutions. But as it turns out, if you are not in the phase rotation invariant case, you have no solutions at all, except 0. 0 is easy to deal with because in the L4 estimate at frequency 0, you don't lose derivatives. Okay, so this means that this part in here that does not have the phase rotation symmetry, all of it goes into this box. And then all you have to do is you have to worry about the cubic nonlinearity, which has the phase rotation symmetry. All right. So this is what happens, at least in the elliptic case. And one thing we realized when we were writing the paper that we just posted last night, the ultra-hyperbolic case, this is no longer true. So there you have some interactions in here that are both non-transversal and resonant. And we have to deal with those. And they're not fully transversal, but they have a little bit of transversality. So there we invent a new box. We call it weakly transversal. And then we have to deal with those expressions. I don't want to go into that, but that's one difference between the elliptic and the non-elliptic case. All right. And I'll come back to this a little bit later. And now let me tell you about the density flux identities in this case. Maybe I can use some of this. Not so much, really. Okay. This happens in the constant coefficient. So I want to give you a quick idea of what happens in the constant coefficient case, because then I want to tell you what bad things happen when you look at, what are the bad things that happen when you look at variable coefficients. So here you have the mass, which we know, but instead of the momentum, you have instead of the single momentum, you have a momentum for each direction. And then dt of m is equal to maybe dj pj. So here our operator is Laplacian, so raising indices does nothing, but I'm preparing my notations for the variable coefficient case. All right. maybe this is also a good place to make another comment about the momentum. So everybody knows what the momentum is, right? And if you write the Schrödinger equation, there's two ways you can think about the momentum. One way you can think of the momentum as the flux of the mass, okay? And the other one, if you take the Hamiltonian interpretation, you can think about the momentum as the generator of the group of translations, right? Funny thing is, this is not one and the same thing, unless you're working exactly on the Schrödinger equation. And so when we move on from Schrödinger equations to other equations, like I was telling you about our results for other dispersion relations, you have to be very careful what you call the momentum. And for us, the momentum is always the flux of the mass, is not the Hamiltonian of the translations. That could be very misleading when you try to do computations on a problem like this. Okay, so this is what happens for the flux of the mass, and then you have the flux of Pj, and this is a decay of something that we call Ekj. And the way we work with this, like I was telling you, integrations by parts are sources of errors, so we don't do integrations by parts. We write everything at the level of the symbols. So the symbol for Pj, psi and eta, this is, if you want, minus psi j minus plus eta j. And then the symbol of Ekj of psi and eta, these are the two frequencies. So now these are vectors before they were numbers. This is psi j plus eta j times psi k plus eta k. All right. So now this density flux relations are what go into the interaction Moravec functional. So if we have two solutions to two Schrödinger equations, if you want, the interaction Moravec functional gets a little bit more complicated here. So this will be an integral over two variables, x and y, same as before, and u is associated with x, v is associated with y. But now here we have some weights, aj of x minus y, make this translation invariant, m of u p j of v minus m of v p j of u dx dy. And of course, the interesting thing happens when you take the time derivative of this interaction Moravec function. So this is supposed to capture how much these two solutions u and v interact. All right, and so I'm trying to decide if this board is enough. So what happens when you put the time derivative in here? The time derivative doesn't fall on a, falls on each of these two guys. It converts into an x derivative or an y derivative because of the density flux relations. You integrate by parts. Put this derivative over here, but it's just one integration by parts, so maybe it's forgivable, right? And so let's try to fit it in here. Of I of u and v is integral. And so now I end up differentiating this aj, but I end up differentiating it with respect to another of the variables. So let's call that guy ajk of x minus y. And here I'm going to have something like m of u e jk of v plus m of v e jk of u minus 2 times p j p k of u. And so this is a 4 linear form. And for this 4 linear form, we can write down the symbol. Okay, so let's call this, before we had the J4, which was a scalar object, let's call this G4 JK. All right, and now I think that can go. You do the computation. This is like linear algebra. And you write down the symbol of G4, J4, JK. And let me put the indices down so that whatever happened bad before doesn't happen again with the indices over there. All right, so this would be equal to, let's say, psi 1j plus psi 2j minus psi 3j minus psi 4j multiplied by the same expression with the k index, psi 1k plus psi 2k minus psi 3j minus psi 4 also k. Okay. And so when you integrate these expressions, you care about these symbols primarily when these symbols psi1, psi2, psi3, and psi4 add up to 0. And so if you do a very naive computation, you can write down that this J4 JK let's see, I want to write it, what's the best way? Right, so I want to write it as maybe psi 1j minus psi 4j multiplied by something like psi 2k minus psi 4k. This happens on, let's say, delta 4 psi is equal to 0, this diagonal set that I was telling you about. All right, and so this means that at the leading order in this computation, you're going to get integral of ajk of x minus y. And then you're going to have some expressions. So 1 comes from u, index 4 comes from v, 1 comes from u without bar, 4 comes from v with a bar. So you're going to get something like dj u times v bar minus plus u times dj v bar, and then the same expression here with the index k. And so if you want to have some positivity in here, you look at this expression ajk, you would like this to be positive definite, and this brings us to the source of weights that we want to put in here. So we would like maybe aj to be dj of some function a, where we assume that a is convex. All right, and I'll tell you in a moment some good choices in here. But if you look at the interaction Moravec's functional, the other thing that you want to know is you want to be able to directly estimate what is I of uv. And for that, since we only control Sobolev norms in here, you need to know that aj's are bounded. So A is convex should also be Lipschitz. right? And then my notation would be AJK is equal to DJ dka. And in effect, in the computation that I did before, I have already assumed that AJKs are symmetric. All right, so let's say we give a name to this guy. Let's call this guy Fj, following Fabrice's notation. Then let's see. I can erase this board. Then what you end up getting is something like d dt of I is equal to integral a jk of x minus y fj fk bar d x dy. And so here's one important difference between this computation and the computation in one dimension. In one dimension, when we did this derivative, we ended up with a one-dimensional integral, but here we still end up with an integral in both x and y with respect to this weight ajk. And then you have another simple identity, which is that if you try to write down, let's say, fj square, which appears when you diagonalize this expression in here, you can write this as another square, which is something like dj u times v minus u times dj v square, and then plus, and you have something like dj u square dj of v square. And so this means that when you look at this expression, which we're going to define as our new J4 functional, we can write down a nice inequality for J4. J4 of u and v is greater than or equal, neglect this term for now, integral of ajk of x minus y dj u square dj v square. You'd like to take advantage of this, but to take advantage of this, you need to have a sign. And the way you can get a sign in here is if you assume that u is equal to v, which is something we're also going to run into a little bit later. But if we set u is equal to v, and if we make a reasonable choice for this a, so we take the simplest convex function, which is Lipschitz, absolute value of x, then you have some homogeneity, right? This is homogeneous of order minus 1. You have two derivatives, so it's like an operator of order, like a kernel of order minus 3, which gives us a symbol for the corresponding multiplier of order 3 minus n. And so then this expression, J4 is greater, J4 of u and u, you get that this is greater than norm of d to the power 3 minus n divided by 2 u square L2 square. And in effect, this is, well, you have an identity between this guy and this guy over here with some constant that depends on the dimension. So you might say, oh, this looks a little bit like what we had in one dimension. In one dimension, we had J4 greater than the derivative of u square. But there's a key difference in here. This is an inequality, and J4 is a stronger expression somehow than the expression that you put in here. And that's not a problem here because we have an inequality, but when we go to problems with variable coefficients, and in particular our quasi-linear problems, what happens is we produce errors at the level of J4, but we can only control errors in terms of this expression in here. And so if you don't do things really carefully, your errors will be much stronger than what you have to control the errors. So in the higher dimensional case, as it turns out, it's more difficult to control the errors that you make coming from variable coefficients than in one dimension. Okay? So maybe so let me tell you now what are the density flux identities in the variable coefficient case. For the paradifferential equation. And so those will have the form. So now we define, if you want, Pj with the raised index. This will be G, let's say Jk plus lambda Pj lambda. So we raise the index with respect to the metric, and the metric will depend on our frequency truncation lambda. The same thing we do for Ejk. We also raise the formula that we use the same formula for lower indices as in the constant coefficient case, but then we raise the indices with respect to the metric associated to the frequency lambda. We write the density flux relations. So we still have dt of the mass frequency lambda is dj j lambda. Plus, and so here we have some source term, and where's my paradifferential equation? It's over there. So I'm looking at the equation with the source term f lambda. So here you have a source term g, if you want lambda, and this g lambda is the imaginary part of let's say v lambda, sorry, the real part of v lambda f lambda bar. And then you write down the density flux relation for the momentum, dt of p. So now I want to put here the index up. It becomes really important. And p j lambda is equal to d k e jk lambda plus, so let's say this was associated to the mass. Here we have a g m associated to the momentum p j lambda. If I try to write this guy, it gets a little bit more complicated. So you have something that looks like v lambda times gradient times derivative of f lambda, or f lambda times derivative of v lambda, plus, and then you end up with some other terms in here. And those terms will be of two kinds. You're going to have something that looks like, let me make sure I don't mess them up, something that looks like derivative of v lambda times derivative of g times derivative of v lambda. And then you also have something that looks like dt of v lambda, derivative of v lambda times dt of g times v lambda, something like this. Okay, so now this is the point where we have to decide what do we do with the source terms? Because when we take our nonlinear equation and we write it in the paradifferential way, the price that we pay is we have lots of source terms, and the source terms get fed into the paradifferential equation. And how do we measure the source terms? And something that I emphasized in the one-dimensional case, whenever we have source terms in the density flux relations, the source terms, we'd like them to have them estimated in L1. Okay? And so in order to do this, we'd like to know that V lambda F lambda belongs to L1. All right. Then you have to allow for frequency localizations, which means that you have to allow for translation, for invariance with respect to translations. And so we define this functional I of, let's say, V lambda F lambda to be the supremum over x naught of the norm of V lambda F lambda x naught in L1. All right? And this is the quantity, this is our key bound for the source term. It's a bit funny because we're asking for a bound for the source term which depends on the solution itself, a little bit like we had it in the one-dimensional case. The key point is that controlling this guy gives us a good handle on the source term in the density flux relations. And because of this, it allows us to prove, to go through the interaction Moravec estimates without knowing more somehow about these source terms. And in here, you see also what happens for the extra source terms. This is G less than lambda, okay, with a square bracket, but that doesn't matter so much. When you look, for instance, at this expression in here, the constant component of G goes away under the differentiation. So this expression is at least quadratic. So this guy in here is like U less than lambda multiplied by derivative of U less than lambda, and could be higher order terms also, we don't care. And so now in this expression that you have in here, this is something quartic, 1, 2, 3, 4. You have two lambda frequencies and two smaller frequencies. And this is something that you can handle using two bilinear L2 estimates. So this in particular tells you that this kind of source terms are good source terms from the perspective of this functional that we use to measure source terms. And so our contention in the end, we can call this a theorem, says the following. And I don't want to erase that. I don't want to erase this. And I don't want to erase that. I really don't want to erase anything.
Maybe
yeah, maybe I can erase that. This one. So let's call this a theorem. And this is bilinear estimates for the paradifferential equation. And so this theorem says, we already have the estimates up there, but now suppose I have two solutions to the paradifferential equation, and I'd like to say I have the unbalanced case. Let me make a definition first. So let's call d lambda, so this is like our frequency envelope, but now for the paradifferential equation, d lambda square is equal to norm of v lambda of 0, let's say in L2 square, plus I of v lambda f lambda. Okay, and now my contention is that bilinear estimates hold with C lambda, lambda minus S, replaced by d lambda, right? So d lambda is like a frequency envelope. It plays the same role as the frequency envelope, except that this corresponds to L2 data as opposed to HS data. So I'm not going to copy again those estimates, but those are the estimates. You have to be careful in here. In the estimates, you have to take the estimates where you put two V's, and then you also have to estimates where you put a U and a V. Both have to hold. So you have, if you want, V bounds, and you have U V bounds. All right, and in the hypothesis of this theorem, you put all the bootstrap hypotheses that you have for your U lambda. Okay. Okay. So I don't have a lot of time, but I wanted to. To point out some of the bad things that happen when you try to carry out this argument that's very, very clean in the constant coefficient case. And so, so there are maybe two difficulties that arise. One difficulty is that in your one integration by parts, you could have derivatives that fall on the metric. Okay, so you get extra terms with derivative on the metric. And the worst thing that could happen, actually, is that you have two different metrics. You have the metric, so one, you could have derivatives on G. And two, you could have G, copies of G, copies perhaps of different G's evaluated at different points. So you could have you could have expressions that look like G, let's say less than lambda of X minus G less than mu of Y. And that's and it's not just Y by itself, plus your translation factor. And so let me write some of those terms that you have in which appear when you write down your J4. So you have something that looks like AJK, the same as before. You have V lambda square times dg times v mu times derivative of v mu square. And then you have terms that look like ajk times v lambda square times, let's call this expression delta g that comes from here, so that it fits on this board. And then you have maybe two derivatives of v mu square. So this is something like you might see in the E's, and this is something like you might see in the P's over there. And so one additional difficulty compared to the one-dimensional case is in the one-dimensional case, once you do your integration by parts, you collapse x and y together. So in the one-dimensional case, x and y are the same. And here, x and y are no longer the same. And the relation between x and y is intermediated by this ajk. So you could have differences arising from the dependence of ajk on x minus y, and differences arising from x0, and that's a big headache, and that's quite a few pages of computations, and you need to, when you look at these error terms, you have to separate them depending on the size of x minus y, relative to x0 and relative to these frequencies lambda and mu. So a lot of work goes in there. But at the end, and maybe the single most important thing when you do this interaction Moravec computation is to do what I formally did on that board and to do it in a covariant way. And if you do the computation properly in a covariant way, then somehow you magically make your errors appear only at the level of this kind of expressions in here and not at the level of the full J4. So this way you avoid the really impossible to bound error terms. If you try to do the computation and think of your operator as a perturbation of the Laplacian and do the naive thing, you're going to end up with errors that you cannot handle. And like always, when you do things geometrically, it's a little bit better. All right. So this is the theorem about the bilinear estimates. And then there's a second theorem that tells you about the Strickard's estimates. And I will, for now, I'll state this theorem in 2 dimensions. And it's going to look a little bit funny. And the explanation for that is going to come on Friday. So this is also for the paradifferential equation.
If I may ask something. So when you want to get the unbalanced bound, you also get them through what's on this board, or you go back to the equivalent formulation of...
Thank you for the question. Right, so I should say 2 things. The unbalanced case, as always, it's easier. And it's easier in several ways. One way the imbalanced case is easier is because these differences of the metric are not important anymore. All you care about is transversality. And waves with frequency lambda move with frequency lambda, waves with frequency mu move with frequency mu. This guy stays separated. So this means that you never worry about the difference between the metrics themselves. You compare each copy of the metric with the identity, and the error, you put it in a perturbative box, number 1. Number 2, actually what happens, and if you take a look at our latest paper, we implemented this idea. When you do unbalanced interaction Moravec, we simplify our interaction Moravec functional and just put 2 masses in there. And then, so our unbalanced, if you want, I lambda mu becomes integral a of x minus y, aj of x minus y, m of u, m of v. All right, we compute the derivative of this, so it gets a lot simpler. And then we could still use a is equal to absolute value of x, but what happens is we foliate this absolute value of x as the integral of x dot theta d theta, where theta is in S1, and for most thetas this contribution, for all thetas the contribution is non-negative, but then we choose to show that this contribution is strictly positive for directions theta, which directly measure the separation between the frequency supports of u lambda and v mu. And since, to give you a fuller answer to the question, let's say we have this picture with a small annulus inside and the big annulus outside. You're going to argue that I cannot separate this small annulus from the big annulus in a definite direction. So then what we do is we take the big annulus, we chop it into angular pieces, and then if I take one angular piece in here, I can separate this from this by a hyperplane, and then we're using an open set of directions theta in which these 2 objects are separate. Hope this answers the question. And that makes the computation simpler, actually, and more efficient. Okay. So I was about to state the Strickard's estimates. And I'll state them in 2D, and I'll state them in 3D and higher on Friday. So this theorem says that if I'm looking at, let's see. Okay, let me, this will require a little bit of a leap of faith. So I want to estimate V lambda. I'm going to estimate V lambda in two ways, L infinity L2. So this is the energy norm. And the second guy that carries a factor of lambda inverse is norm of V lambda. Okay, I didn't explain this, but some of you know what this is. So this is V2 associated to the Laplacian. And this is smaller than. And on the right-hand side, I want to put the initial data of 0 in L2. Then plus, I want to put my sort of interaction functional between V lambda and the source term. So I of V lambda F lambda to the power 1/2, just for homogeneity. And initially, we were hoping for this only. It turns out this was not quite enough. So we put here one more term, which is lambda inverse norm of F lambda in the space of d V2 delta. So these V2 spaces are some replacements to the XSB spaces associated to the Laplacian. So this is something I introduced about maybe 25 years ago in the context of the wave equations, but this is the Schrödinger version. This is with respect to the constant coefficient operator. So when you write this estimate, and if you look at the difference between G, let's say less than lambda minus the identity, you want to put this difference in the perturbative box. And this is not so easy to put in the perturbative box, but one thing that we have already had to do for the interaction Moravec is to estimate this interaction functional in here. And then this term is not so bad because here you are allowed to lose one derivative. And a priori, this comes with multiplied by two derivatives, so you lose two derivatives. And by using bilinear estimates, you can narrow this loss to one derivative. And so that's what makes this work. And so if you look what this expression on the left controls, this controls exactly lambda to the power 2 over p norm of V in LP, LQ. This is the Strickard's norm, lambda to the power minus 2 over p. And in the particular case, when p is equal to q is equal to 4, our loss is 2 over 4, which is 1/2 derivative loss. And a loss of 1/2 derivative is big, okay, from the purpose of doing estimates. So what you have to remember somehow is that this L4 estimates, in the way we have our setup, we only use the L4 estimates in the context of the balanced interactions. So we use L4 estimates for maybe 4 frequency lambda entries. And for each of those 4 frequency lambda entries, I have my number of derivatives for the initial data to control them. So that's sharp only at scaling. And the more I am above scaling, the more this 1/2 loss becomes less important. And so that tells you that using this L4 bound, you get something, but not the sharpest result. Okay, and I still maybe should have said something about what we do in the low regularity case in 2 dimensions. That's when we assume that the equation is conservative. That's a computation which is akin to the division problem that we talked about in the 1-dimensional case, but it's a slightly simpler division problem that we have to solve. So we have this C4 of U bar, U bar form that arises in the density flux identities. And now we'll know that C4 is symbol of psi is equal to 0. And this means that we can write this C4 algebraically as maybe psi even minus psi odd times something plus delta 4 psi times something else. Delta 4 psi is something that contributes to the flux, and psi even minus psi odd is something where you're allowed to use the balanced bilinear estimates. So maybe I didn't quite do justice to this two-dimensional result here. I didn't have time to show you too much of the details, but you get the ideas. The ideas are you write everything in density flux form, your conservation laws. You optimize them whenever possible, and then you do very carefully the interaction Moravec's estimates in covariant way, and spend a lot of time estimating errors, trying to close this bootstrap loop. Okay, and like I said before, this is easier when you see it all done. But every time your argument is a big bootstrap, the question is what you put in the bootstrap box and how you recover that, and that's a long trial and error process. So that's it for today. I think I'm right on time. We had a lot of questions, yeah.
I think it was pretty clear.
So, yes, so you mentioned, the first lecture you mentioned 1 and 2, but in fact here you mentioned 3 and higher.
3 and higher,
it's easier.
It's easier, right. And in effect, even in dimension 3, there was no result of this type. Okay. In dimension 4, there was a paper that we wrote maybe 2 or 3 years ago with Jiaxi Huang, where it's a nice result, it's a global result, but we were not very sharp with derivatives. We did not use this interaction Moravec technique, we didn't know it then, and just some S. Imagine S maybe about 1 derivative and a half above scaling. For a very specific model, not for a model with a lot of structure. So and that was dimension 4 and higher. So even in 3 dimensions, we're not aware of any quasi-linear results of this type.
And okay, at some point in the theorem, you say at least we can handle only when we are in the conservative and the conservative phase.
Right. That was this explanation I gave at the end. So in dimension 2, at low regularity, this 1/2 derivative loss in the L4 bound is too big to handle low regularity. So we have to discard the L4 estimate, and instead this conservative assumption tells us that this symbol of the quartic form vanishes on the diagonal.
Good. Thank you. But if not,